Hey, what's up, people? Now, I know that some of my more regular viewers have probably been asking themselves, like, hey, where'd that fool go? It's been like over a month since he's posted a video. Yeah, there's sort of a reason for that. And I did mention in the previous video that I posted that I had been working on this box that was going to house all the hardware to run a light show, and specifically like a Christmas light show, although it can be used for other things like for Halloween, for example. And so that consumed a lot of time. I will talk more about that in a future video, as right now it's still operational, so I need to pull it off the wall in order to, bring it to the bench in order to be able to like explain everything. But today I actually wanted to talk about these little guys, which I'm actually employing 3 in said light show. And they've been working pretty well, and I thought they were interesting enough to talk about. The shape of it, it's kind of like an IC, and it's very reminiscent of some sort of a power device. And if that's what you guessed, then yeah, you would be kind of right. So what these are is these are QTT3213s, and they are zero crossing high powered Triac optocouplers. And if we zoom into it a bit, we can see that it's basically an 8-pin dip package, but instead of having the legs go straight down, they are bent out to the side. So now it's a surface mount device. And so I got these not because I wanted to specifically use them for controlling Christmas lights. What I got these originally for was because I had a 3-speed fan that I had bought that I was trying to modify to work with ESP Home. And so what I wanted to do is have an ESP like 8266 module connected to, initially I was thinking of connecting it to some relays, and then the relays were going to take care of, selecting high, medium, and low. And when they're all off, the fan would be off. But I had these 3 that I intended to use, but these are 24-volt relays. And while they don't require a lot of current to operate, I was trying to find a small switching power supply module that would be powered directly from mains and provide the 24 volts to run these. I couldn't really find anything suitable, and I was trying to make this thing as small as possible. So I thought, well, I'm not going to use the relay idea. And so then I thought, well, I could use 3 Triacs, for example, like this. This is an MAC15MG. These are 15 amp Triacs, rated up to 600 volts, I believe. I don't know if this one's 800 or 600. Either way, I don't need that much. We'd only need up to like 120. So I could use something like this, but then I would have to couple them with some optocouplers for controlling the low voltage side, and for switching the high voltage side that these would be connected to. But not only that, I also wanted to employ some zero crossing circuitry on the Triacs side, so that the Triacs could only come on when the because it'd be running AC, so as you know, it'd be like a sine wave. So when it crosses that 0 voltage point is when the circuitry would allow the Triac to turn on, and then that way it sort of like ramps up the power to the coils in the motor a little bit more softly, instead of being able to have it turn on at like the peak of its current, and then it just kind of hits the motor kind of hard. But it probably wouldn't damage anything to have that be the case. But I was just trying to make it so that it'd be a little softer. And that's when I came across these guys. So these are basically everything that I wanted to do with a bunch of external components, all packaged into one tiny 7-pin device. And if we take a look at the datasheet for it, that's what's basically inside of the package. So that's the Triac. This stuff is the zero crossing circuitry. That's the that looks like another Triac inside. That looks like that's what's receiving the signal, or the light from the emitter side of the circuitry. And so that's, works with that to trigger the Triac, so that it only triggers on at that zero crossing point. We can see that on this side of the device, we have what's main terminal 1, main terminal 2. Those would be the lines going to the AC mains. And we have a G, and I'm pretty sure this is not ground. I believe this is probably gate, although I'm not entirely sure, and it doesn't, I went through this data sheet, it doesn't specify what the G actually is. And so on the other side, we see that we've got 3 C's and an A. This sounds like my grades. But So the three C's would be the cathode, and the A would be the anode. So this would be the positive side of the internal emitter, and the C's are the cathode. So we just need to provide a small current and across like the A and one of the C's, and that's what would allow the output side to turn on. And because all that stuff is built into the package, it makes it really easy to use, and it requires very few external components. And so what I thought was, wait a second, I can use these to control some dumb strings of Christmas lights. And so I had intended to use some like wrapped around some two bushes that we have, and I really didn't have any other way to control them without to make them part of the light show without having some sort of other external device that could turn them on and off. The only other option was also going with relays, but the thing is that they'd be frequently like turning on and off. So I don't know if having some relays in there would appreciate the frequently like turning on and off. So this is what I used. And so what I did is I took these, I made two of these boxes that I had. These were originally fan speed controllers. They had a switch on a knob, and so with a potentiometer. So if you turn it all the way counterclockwise, you'd click the switch off, then you click it on, and it goes through a high, medium, and low. But I took the actual controllers that were inside of these out, and I used them for something else. So I had these boxes laying around. And so if we open this up, you can see what I did. So there is the device. That's just one of these. And so what I did is to keep things very simple is you can see that there is a wire going from what would be the live terminal from the plug side. And it looks like it goes through a wire going off into the main terminal one side of that optocoupler. But there's actually a pico fuse inside of the sleeving. I used some heat shrink to sort of sleeve it in there. So it's just a 2 amp pico fuse. I wanted there to be some protection from the input, to the output. If something happens, then this fuse would blow and just cut off power to the entire thing. And so I've got the neutral side going to another wire, and that wire just runs directly to the neutral side of the outlet that goes connected to the lights. I left the ground intact because it's just grounded, even though the Christmas lights themselves don't actually use any ground. And so on the emitter side of the optocoupler, we can see there's a resistor. And then we just got two wires going to the outside. So I just have a positive and a negative. And the resistor that I chose to use for this was a 1K resistor. And I went with 1K because that at 12 volts provides about 10 milliamps of current to the LED, which should be more than sufficient to get it to properly turn on the output. I found through some testing that these will actually operate to some very, very low currents. So this is it. That's basically all it is. If I just kind of cover this up so I don't expose anything, we can do a quick little test. If I get this outlet, this is plugged into mains. So if I plug this in to that outlet, and then I've got this light on this base, and then I've just hooked up a plug to it. So I'm going to plug that into the outlet side. And so now if I apply a voltage to these two pins, I can get this light to turn on. So I've got just a 9-volt battery sitting around that I can just take. I'll hook the black to the negative, and if I hook up the positive to the positive, it just flickered. Oh, this battery's dead. Well, that was weird. I could have sworn that was a good 9-volt battery, but it was completely almost flat. It just had barely enough current to get this thing to just flash on the way we saw there. But after that, it had nothing else to give. So this is a good 9-volt battery now. And if we do that again, we can see that we can turn on the light bulb and that it stays on. So basically, that's all I'm using these for in my light show. And the thing is, though, that it doesn't just turn them on and leave them on like this, and then turn it off and turn it on. The light controller is actually controlling them to be able to dim and stuff. But these optocouplers don't exactly dim the way that I would, kind of would want them to, maybe. So instead, because of the zero crossing circuit, they end up doing a little bit of funky stuff, and I'll try to explain why exactly it happens. And it's not exactly the most desirable outcome, but it sort of works for Christmas lights just due to the fact that usually you have a lot of stuff like twinkling on and off and stuff like that. Although it would not work if you needed to be able to like linearly dim something and, bring it back up or whatever. Now, what I'm actually using to control the optocouplers is one of these boards. This is a DMX board. They're numbered WS-DMX-8CH. And what this is it takes DMX data, which I'm not going to go into in this video. I'll probably explain it a little bit better. As well as I know it in when I do the video about the light controller. But basically what this does is it takes an input of data, and the chip basically takes that data, decodes it, and you're able to control a total of 8 outputs on this side. And so this can control 2 sets of LED strings with white, blue, green, and red channels outputs. And then we have another set of white, blue, green, and red. So, and then we've got the voltage positive and voltage negative. There's also another voltage positive on that side. So I configured this so that in the software that runs the show, it can turn on and off some of these outputs. And so I've got 3 in use, and they each one of those goes to one of these outlets. One of them is not in one of these boxes. I actually embedded it into a light up Santa. So that's built into the Santa at this point. But the outputs on this controller don't just turn on and off because they are normally meant to control LEDs. They turn on and off rapidly. So that's how they're supposed to be able to dim and brighten the LEDs that you're just connected to. But like I said, because of the way that this works with its zero crossing circuit, they don't exactly play very well, or play very well. But kind of slurred there a bit. So I'm going to grab a piece of paper, see if I can draw a diagram that makes sense as to why it causes lights to twinkle the way that I mentioned. I'll try to explain it as best as I can. All right, so let's go ahead and give this a shot. Here we go. So one thing to keep in mind is that none of this stuff is drawn to any sort of scale or time scale or anything like that. And so I've got 2 charts basically. And so on the top, we've got basically what would be our 60 hertz sine wave from the wall mains. And I've got this labeled as 120 volts positive and 120 volts negative, when in reality, this should be closer to like 170 on both ends. But just to keep it simple, we'll just say it's 120 volts. And then on the bottom, we've got what would be the pulses coming from the DMX board into the Optoisolator. And this is technically grounding out the LED outputs. And then we have a common positive. For simplicity, I just put on here that we have on and off. So it's whenever the emitter inside of the optocoupler would be on, then we've got like a positive pulse. And then when it's off, we've got a negative going pulse. So there's a few other things that if you required like some specific timings that you would take into consideration regarding like Triacs, whether it's this or this one. And one of the things is the holding current. And what that is if you're running say you're running a DC current through one of these devices. Well, once you trigger the gate to turn on the Triac inside, it's going to keep conducting no matter what you do to that gate until the current that's flowing through it drops past a certain point, which is what the holding current is. And then at that point, then it'll stop conducting and you can once again trigger it to turn it on. In the case of something that's going positive and negative, once it goes to the like that 0 point, it's going to stop conducting. So you could trigger this, but as long as the current going through it is AC, it's going to turn itself back off at some point. And so the same is true for the Triac inside of this device. So that's one of the things that's going on in this chart here that I'll explain in a second. So let's see what we got going on. All right, so as I mentioned, this would be our a representation of our 60 hertz sine wave. And then let's say that the controller turns the output or turns the input to the optoisolator on. But say it falls into this period of the 60 hertz mains current. So we can see that it falls somewhere in between where it's going maybe like halfway up to the 120 and just about the peak. But because we don't have any zero crossing at that point, the light or the output is not going to turn on. And as it goes down, if we say we have another pulse where it would normally be turning an LED on, if that falls right in between that point and right before it actually reaches the zero crossing point, it's still not going to turn the output on. So once that starts going negative in the other direction, let's say we have another pulse and this also happens in between like that point and that point, we're still going to get no output. Now, say we have another pulse that's maybe a little bit wider or just happens to fall right between the points where this is about to hit the zero crossing and a little bit after. We can see that at this point, because we have the input to the isolator on, we're going to get some conduction from that triac. And even though at this point, the input to the isolator is turned off because we have that holding current through the triac, this is going to continue conducting current until it gets to the next zero crossing. But then if we have another pulse that happens just before that zero crossing, and even if it turns off like right after the zero crossing point, because there was still current and or the gate of the triac being triggered, it's going to continue conducting. So it's going to continue even though it's the pulse has already turned off. It's going to continue with the holding current. It's going to get to this point, and if at that point there's another pulse that's going to fall right in between that zero crossing, then it's going to continue conducting. So at this point, we kind of have like a one cycle and then half of a cycle. But if there's nothing else to continue keeping it on, or if we don't have a continuous, just on current that's going to make this just continue conducting the entire time, then we're going to get to this point once it gets to zero again, where it's going to stop conducting. So then the current is going to go in the negative direction. It's going to go back up. At this point, we have another pulse that falls right before it gets to zero crossing and just after. So the triac is going to start conducting again until it gets to the next zero crossing. And even if we have another pulse during that period of time, but it stops right before it gets to zero crossing, then it's not going to continue when it gets to that 0 point. So we could have this situation where we have like a cycle and a half, and we can be missing a half of a cycle, and then we have another half of a cycle. And so right there, I've got another pulse, but because it's right in between, or it's inside of two zero crossings, this is not going to allow the triac to conduct, so it's going to remain off. It's going to remain off. And at this point, we have another small pulse that would be right before the zero crossing. So right as it gets to zero crossing, it'll start conducting again, and it'll remain conducting as long as the holding current is above a certain threshold. It gets to this point, it turns back off. So, and then we have another pulse there where, it's going to fall like after the zero crossing. So it's not going to turn it back on. And then we can have this going back down. We can have another pulse that's going to turn it on just before that zero crossing. So then it's going to start conducting again. So this creates kind of a weird situation where we can have half cycles happening on the triac side of the optoisolator. And I think I've actually observed like physical or visual evidence of something like this happening when I was testing the lights that I'm talking about. They are strings of LEDs, but it was doing some weird things where some of the LEDs would be on and some of them would turn off, even though it looked like, it was supposed to be on. But I think it's because we have situations like this happening where only like half of some cycles happen to trigger just at the right time, where it causes the funky behavior that I was talking about. So yeah, this is just like a basic explanation. And as I said, for, stuff like Christmas lights that are kind of meant to like twinkle and stuff to begin with, this will work. And it causes like a bit of like random like flickering. But if you need a little bit more control for something and stuff like this is just not going to fly, then yeah, this is not the right device to use for something like that. One thing I keep forgetting to mention about this device is that it's only rated for up to 1.2 amps continuous. There's a few other versions of this that handle a little bit less current. I went with the 1.2 amp one because, as I said, I wanted to use it for a fan motor, which also doesn't draw like a ton of power, but 1.2 amp should be more than enough. If you do require something that needs more current, then you probably still need to go with something like this other device, this TO220 package. I couldn't find any other similar devices that could handle any more than 1.2 amps. So as far as this device goes, that's pretty much it. That's all I wanted to really talk about. But I did want to test the whole whether this is a gate input or not on the bottom, the 5th pin. And I wanted to do that by using this is one of those dimmers that you would normally, like find on a wall. And so this one you turn on by pushing the plunger in, and then you adjust the brightness of whatever light's connected to by turning the shaft. I don't know which position is off and which one's on at the moment, but normally this would be using a Triacs similar to the one that this MAC15MG that I've got on the bench. But this one is, as you can see, it's riveted directly to the case. And you'd think that, well, isn't that kind of dangerous? Wouldn't the middle pin be connected to that and you got like mains going through that device? Well, one little important thing to note is that the ones that are usually used in dimmer devices like this, they have an isolated tab. So if I pull out the multimeter, I'm not going to bother trying to bring it up on display or on the capture, but if we check the resistance between the tab of this device, we can see that we've got pretty much full continuity between the two. But if we check it on this device, we can see that the tab and the middle pin, they have absolutely nothing connecting them together. So these devices are isolated, and it's kind of an important little distinction between other Triacs that you can, like buy versus what's used inside of these devices. And so what I've done is I took as you can see, I've disconnected the original Triac. I took one of these and I put it in the place of that one exactly the same way that it would be wired. And so I want to see what happens. Hopefully it doesn't go exploding on us, but I'm just really curious to know what happens. Normally, this little diode-looking device, let's zoom into it a bit. So that tiny little blue thing, not the big one behind it, this is a diac. So this, as you're adjusting the potentiometer, it's raising the voltage at that point, but these are usually rated to like 36 to 40 volts, I believe, or so. So it doesn't actually conduct anything until it sort of hits that peak. And so, yeah, let's just see what happens. We'll wire this in line with that bulb that I showed earlier. But actually, before we do that, through the magic of just happening to have another one on hand, this one was a brand new dimmer. Let's get a baseline of what this bulb, looks like, even though I'm pretty sure everybody kind of knows what a dimmer, how it works. But just so that we can get a reference, let's connect this in line. All right, let me just say that this is, everything's sort of like really well covered, and this is, the plastic case is still on it, and there should be no power going through the casing, but it's still a little bit on the dangerous side. So if you don't know what you're doing, don't be trying stuff like this. I'm just doing this for the sake of the demo, but I'm going to bring in the outlet, and let's see. Okay, this one turns on by turning the shaft clockwise, and I've connected these in a way that I can connect, because this isn't a polarized plug, but I made it so this side is the neutral, so that's how I'm going to connect it. The live side is the one that goes through it's going to go through the dimmer before it goes to the bulb. So plugging that in, and I got to plug in the other end of the extension cord. Okay, there we go. So as I turn this on, the bulb should start glowing as I turn the shaft clockwise. There we go. So as you can see, it gets brighter, and the camera's going to compensate for it, so it's not going to be as visible. But you can see it changing there. So as I go down, I can dim that filament. Look at it's just barely glowing right there. So, and then I can go up and down. So that's how a basic dimmer kind of works. So now let's try the modified one and see what trying to drive what I think is the gate on the optocoupler does. Okay, now I've got this one clamped into those connectors. And as I said, this one's a bit more dangerous just because of the fact that there's nothing covering it. I don't want to go and, touch the back of it. So I'm just going to handle it by the aluminum plate in the front. So, yeah, let's see what happens. I'm going to make sure that this is turned all the way down. And I guess it doesn't really matter whether the switch is on or off. Although I could actually verify it by touching these two with the multimeter. I'll do that. Let me just try to get it in the completely off position first. Okay, so now the switch is in the off position for sure. And as we can see, there's a wire that goes to this is connected to the live coming from the plug. And there is a small little neon bulb in the front that normally that would light up the knob. So that's, as long as it's getting power, that should be on. So let's see what happens. And yeah, neutral's this side. Here we go. Okay, so that neon bulb is glowing, meaning that it's got power. And I'm going to push the button. Let's see. And the light turns on right away. And it's not allowing any dimming function whatsoever. So, yeah, this apparently cannot be used like a standard Triac or anything like that on that side. I mean, I'm sure it's got its use, but I'm not entirely sure where exactly you'd use something like that. But yeah, there we go. And with all that, that pretty much wraps it up. And as I mentioned, I'll be talking more about these other things when I get around to working on the video about the entire light controller box. But we'll just leave it at that for now. And so it's right about New Year's. So Happy New Year's to everyone. Thank you all for watching once again. And I will see you guys around the bench.